Hello students, welcome back to the next lecture on classical mechanics, which happens to be lecture number 21. And in the last class, we have discussed what is meant by a central force problem and the importance of the central force problem. In fact, the good idea about the central force problem and the basic information about this must be already familiar to you right from your BSc in terms of the study of the Kepler's problem. So in the master's level, now what we are going to do is that we would like to address the central force problem from the Hamiltonian mechanics point of view, which means that how the Hamiltonian mechanics is providing better insight into the physical problem and then the discovery of the constants of the motion in the problem. So that is first, or that is the main objective of studying the central force problem as an example. The second reason why the central force problem is so important is that in the nature, if you see astronomically, okay, the number of masses on this free space, okay, that means the number of stars, number of planets, whatever you call, they are all the masses, right? Every mass has its own gravity. So the entire universe is made up of gravitating systems, and therefore taken two at a time, we have two-body problem. So two-body problem is the simplest situation that can be solved. Of course, three-body problem is not exactly solvable due to the mathematical complexities. And therefore, we study two-body problem mainly. That the gravitating system is an excellent example of the central force problem. And you have too many of them in the nature. And therefore, it gives you a solid reason why we have to learn the central force problem. That's the first reason. And coming to the smaller scale, namely the atomic scale, if you're going to describe the motion of electron around the nucleus, then once again you have the central force, okay, which means that the electrostatic force is actually 1 over r square, which means that the electrostatic potential is 1 over r. So 1 divided by r is an example of a central potential. Gravitational potential is also 1 divided by r potential. That means 1 over r potential. So in any case, whether you are going to the atomic scale or to the astronomical situation, the central force examples, okay, or too many of them are there surrounding us. That is first thing. And in addition to that, apart from this 1 over r potential, there is another case is very much relevant to the naturally occurring physical systems, namely the vibration of molecules. You take any set of diatomic molecule, for example, like hydrogen. 2 hydrogen atoms are there, which forms a molecule. So if 2 atoms are joined together through a chemical bond, we say it's a diatomic molecule. And this will vibrate because of the 0-point energy. So the vibration is equivalent to a harmonic oscillator. And the harmonic oscillator potential is also a central potential. So now you see that how many number of physical examples, which are too many are there. It is not, even though we say that one example here and one example in gravitating, but overall if you see, in any case, this is the dominating, too many of them are there in the atomic scale as well as in the astronomical scale, and therefore it provides a sound reason why we should study and understand the central force problem. And mathematically speaking, we can always go beyond the 1 over r potential and as well as this the so-called harmonic oscillator potential. We can go away from that and then dump any expression, mathematical expression for the central force and then study the mathematical properties. So central force problem provides an ample scope for both the physicists as well as mathematicians to study and explore their own properties. I mean, physical properties for physicists and geometric properties in the phase space for mathematicians. So you understand at least why the central force problem is so important. And we have seen an introduction in the last class, and for the corresponding two-body problem, in fact, we have drawn the diagram which you have with you. And today's plan I will explain. So let me explain the today's plan. But before that, keep a note on the diagram. So hopefully you have the diagram in your class notes. So today's plan is that keeping the 3 equations, that means at the end of the last class, we have these equations number 1, 2, and 3. And what is the idea, or what is that we are planning to do is that in the last class we have seen that if we are going to use the equation number 3 for further study, then we will be having, or we require 6 degrees of freedom, 3 for the R1 vector and 3 more for R2 vector. So basically for the two-body problem in the three-dimensional Euclidean space, essentially you need 6 degrees of freedom. Okay, under the influence of, this is important, under the influence of a central potential. Okay, with that being the assumption all over, that this we need 6 degrees of freedom. And the plan and the question that we asked in the last class is that can we reduce the number of degrees of freedom by doing some kind of a transformation like coordinate transformation, etc. Okay, that was the thing. And in that discussion last class, we have got an idea that what happens if you calculate the center of mass of the two-body system, and then in case if you are going to use those as the variable, then is there any chance to reduce the number of degrees of freedom? That was the question. And in order to address that, we have calculated, or we have written down the equation for the center of mass. This is the equation. Equation number 2 is the equation representing the connection between the center of mass, capital R, with the old variables, I mean the standard variables R1 and R2. And in the diagram, of course, you have the capital R represented in the pink color line, okay, or the vector. Line means vector. So everything is there right now. So now what is the plan is that let us see, or let us work out and see whether the number of degrees of freedom is going to reduce. So that's the plan. And how are you going to proceed for that is that we are going to eliminate. That means eliminating means we don't want the variables R1 vector and R2 vector in the Lagrangian. We don't want that. But instead of that, that is the meaning of in favor of. Okay, but instead of that, we are interested to bring the center of mass, capital R, and the distance of separation between the two masses, which is script R. That means R1 vector and R2 vector are going to disappear in equation number 3, and in place you will be having a capital R and a script R appear there. So that is actually the plan. And how good this kind of equation is going to be, that's the first thing. And later, after completing the elimination, we are going to ask the question, what happened to the number of degrees of freedom? Okay, that is the actual discussion that we are going to do in the today's class. So let us now take the equation and then substitute. So what do you get it from equation number 1? So let me write down that. So from this equation number 1, here we can say that R2 equal to, so I'll write down that R2 will be equal to script R, or I'll write down like this, is equal to, this is equal to, you take it to the left side here, that's correct. So script R, then plus R1. So I will once again write down that this is equation number 1. Okay, so because it is the same thing, we didn't do anything. So therefore, let us keep this equation for our substitution. Okay, so where are we going to substitute this is that we are going to substitute in equation number 3. Okay, so ultimately our aim is that we need Lagrangian. After that we can do the conversion to the Hamiltonian. So that is the idea. So we will have to substitute this into the equation number 3, namely the Lagrangian. So that is the point. And second thing is that we will also require the elimination of one of the variables. So we will have to substitute in equation number 2. So this equation number 2 also contains an R2, right? That R2 has to be eliminated. So that elimination we will do using the equation number 1. So let me therefore write down for clarity. Okay, even though I'm giving the statement, it is better if you can write down that. So if you are going to substitute, so let us substitute equation number 1 in equation number 2. Then what happens? Let us see. So we will be having like this. M1 into R1 vector. The rest of the thing is a fairly simple algebra, so you can easily follow. Then we get an M2 into R2 will be written down as R plus R1. Then we have that is equal to, we have an M1 plus M2 into the capital R vector. And that's all. So that is the simplification that you can expect, which means that what is the meaning? The meaning is that R2 has disappeared, isn't it? So in this expression, you see R1 is there is an R1 is there. R2 has disappeared. So in this way, we can eliminate one by one, and R1 and R2 we are planning to eliminate. Okay, so let us therefore write down. So that will be equal to. So let us simplify this. So we have M1. So we have an M1 here, then plus M2. We have an R1 common for both of them. And then we have plus M2 script R given by the right hand side, which means that, so from this we can write down what is R1 vector. R1 vector will be equal to, so let me write down this after the simplification. So what is going to happen? This fellow will go to the right side. I'll explain. M2 into script R will go to the right side. That's fine. Afterwards, this M1 plus M2 we have to divide throughout the equation. So we are going to divide M1 plus M2 throughout the equation so that I'll be getting an R1 here. That's what is going to happen. And if you are going to do that, I'll be getting an R here. So that will be an R vector here. Then this is going to the right side. So I'll put a minus. Then this is M2 divided by M1 plus M2. This multiplied by script R. So we will call this as equation number 4. So now what happened is, why do you want to call this as an equation is that we have made reasonably a good simplification where the variable is going to disappear. So what has to disappear and what has to appear? You see here, R1 has to disappear, R2 has to disappear. That is called elimination. Eliminating means we don't want them. Okay, somehow you remove it. But removing means totally equation will not be empty. So that is not the meaning. That is why I am writing down in favor of. When some variables are disappearing, some other variable will appear in place of that or to take care of that variable. And those are the capital R and the script R. So you see that you have the capital R is now appearing in the equation. Script R is appearing in the equation. And what is getting disappeared is the R1 vector. So this is how it is getting disappeared. So now it is clear that R1 is going to be this. And therefore, now we can use the equation number 1 in order to get the equation number, in order to get R2. So what is R2 now? We'll see what is R2. R2 is equal to, for that you should remember equation number 1. So let us go up and see what is equation 1. And remember this, that script R plus R1. Remember script R plus R1. So let us come down. I'll write down that this is script R plus R1 vector. And where the R1 vector is given by equation number 4. So therefore I'll write down, and now you can use the equation number 4. So we are going to use equation number 1 and also we are going to use equation number 4. If you do that, we will be able to get R2 vector is equal to, so let us add this. So this becomes R, then you have a plus R1, we will substitute this, which means that capital R minus M2 divided by M1 plus M2 into the script R. So this is what you have to simplify, and let us see. So if you simplify this, I will be getting, so let us, these two are common. So let us simplify this. M1 plus M2 minus M2. Okay, M1 plus M2 minus M2. How much is that? It's M1 divided by M1 plus M2. The common term is script R. Then we get a plus, get an R. So that is the required equation. Okay, so I am just seeing equation number 4. And now you can see that equation number 4 and equation number 5 has some kind of similar appearance. So now these are the two important equations. I'll just put some kind of a line here so that you can recognize that these are the equations which are going to help you in the elimination process. So equation number 4 and 5 will help you to eliminate R1 and R2, and in place we will be bringing capital R and small r. Okay, fine. Equation 4 and 5 are going to be useful. So you will have to now therefore substitute equation number 4 and 5. So where do you want to substitute? Is in the Lagrangian, in the equation for Lagrangian. The equation for Lagrangian. But what is that equation number for Lagrangian? Is that it will be there? Yeah, here it is 3. So the equation for Lagrangian is equation number 3. So in this equation we are going to substitute. Now when you are substituting, what happens is that nothing will happen to the potential energy term. So you don't have to worry about this. Let us therefore evaluate the first two terms, which represents the kinetic energy. Okay, only you can always attach the potential energy at the end. There is nothing is going to be transformed in the potential energy expression. So let us therefore calculate only the first two terms representing the kinetic energy, and then we can write down the Lagrangian. The equation for Lagrangian, okay, and especially ESP means especially the kinetic energy part. So I'll write down therefore the kinetic energy is given by half into m1 into r1 dot r1, then plus half m2 r2 dot r2. That is your kinetic energy, and we are going to substitute equation number 4 and 5. So let me go back and keep that visible. It will be little, it's occupying the entire board, but somehow you'll have to write down this. So let me therefore write down here. So that is equal to. So let me write down the equation number 4 and equation number 5, and then we can substitute. Okay, that is equal to, because the space won't be available here, so I'll write down here. So that is equal to half into m1, half m1 into r1 dot r1 means basically you are squaring. So let us write down the expression for that. And the expression is like capital R vector minus m2 divided by m1 plus m2. Then you have the script R vector. Okay, and then you'll have to take a square, because r1 dot r1, so there is a square. But there is something important, because this is a kinetic energy term. These are the time derivatives, and therefore I am putting a dot. So you please see now only I am putting a dot here, because these are actually the time derivatives. So r2 dot square kinetic energy, and therefore everywhere you have the time derivative. So you'll make sure that the time derivative dots are present. And similarly for the second part of the kinetic energy, we'll write down half m2 into the expression for r2. So that is actually given by the capital R vector. Then we have plus m1 divided by m1 plus m2. Then you have the script R vector, and once again time derivative, and that's all. The whole square. Whole square is velocity square. So half mv square is what we are writing. And now you'll have to simplify this, and simplification is fairly easy, even though it looks like you are going to use a plus b whole square. So you'll be having 3 terms coming here and 3 terms coming here. But interestingly, what happens is there is a plus here and there is a minus here, and therefore one term is going to cancel, and therefore the equation will be somewhat comfortable. We can write down, not a problem. So let us write down that half m1 into, I will expand it using the simple a plus b square formula. Then I'll be able to get this. Then you get a plus. I'll be getting m2 square. Then you get a script r dot square divided by m1 plus m2 square. Then minus 2ab term. 2ab term means, okay, minus 2ab term. So minus 2ab term means it is 2 times. Then you have a time derivative of r, then dot product of the time derivative of script r 2ab, then I get an m1 plus m2, and that's all. So first term is over. Then plus, you have to repeat this similar term for the second part of that. So that gives me once again r dot square. There is a r dot square, and then plus the second term will be m1 square script r dot square. Then you have divided by m1 plus m2. Then plus 2ab term. Now it is plus 2ab term. So I'll write down plus 2 into r dot into, you have script r, which is a dot product now, then divided by m1 plus m2, and then close this bracket. Okay, and you can always see that the 2ab term is getting cancelled, and what is left out is that we can take something common here. Then I can write down m1 plus m2 r dot square. Okay, which means that this term is there and this term is there. I am taking common, so that is fine. Then is there anything common here? Let us see second term. This is getting cancelled. Okay, so I'll just show that this is going to be cancelled here. I'll show like this. So this will be cancelled. it will be cancelled with this term. So I'll cut this. Okay. So what is left out therefore is that we have one more term here. So let us see what is common. What is common is that 1 by 2 is common, fine. And then we have an M1 and then R dot square is common. So let me write down R dot square, that is common. Okay, if you open this bracket, so what is left out, you see that I'll be getting M1 M2 square. I'll get M1 M2 square. Okay, double tick means this expression, and I'll put here a double tick, and corresponding to this I'll be getting plus M2 into M1 square and the common denominator. And common denominator is M1 plus M2, the whole square. I think whole square is there here, right? You see here, there is a whole square here, and here also, here also you have this particular whole square. So that is the term, and that's it. We don't have anything else. And now this is fairly easy to simplify. And we have, this is equal to half into, and let us make, let us write down, and M1 plus M2. Then you have a capital R dot square. It is always better to have a vector symbol. I already told you why to put a vector symbol when you are squaring. So this is something which I explained in the last class, and you please remember that when you are writing a vector A, usually remember this, when you have an A vector square, what is the meaning? The meaning is actually A dot A. That is the meaning, which means that it is modulus of A and then square here. And this is a scalar. So point to be noted is when you are going to square a vector like this, A, and then you have a vector symbol, namely the arrow, and then square. When you are squaring, you are getting a scalar ultimately. So if you are getting a scalar ultimately, it is just enough if you can write down A square. A square is enough. The question then is that why do you want to write A square? So that is the point that I am trying to explain. The point is that if you write a vector there and then it gives you an information, or it keeps your memory active, saying that you need 3 components for that. So that kind of information should be always remembered, because when you are counting the number of degrees of freedom, we have to be careful whether 3 variables are there or just 1 variable is there. If you are going to say simple A square like this, at the end of the day, you think that only one number is enough, A here. But it is not so. If you want to calculate A square, we need 3 components: X component of Y, X component of A, Y component of A, and the Z component of A. So in order to keep your memory, keep informed that you need 3 numbers for that, it is a better practice to put a vector here and then say that it's a square. Okay, we know that it's a scalar quantity, but I'm explaining purpose of putting arrow on top of the vectors. Okay, keeping the arrow is it will keep you informed. That is the point to be noted. And then coming to the second term here, you have a plus. Okay, so now I think you can simplify this. If you take M1 into common, then I'll be getting half into, you will be getting an R dot square. And this term, if you simplify, I'll be getting M1 into M2. Okay, divided by 1 M1 plus M2 will be cancelled, and therefore I'll be having this kind of an expression. And that's all. And almost over. There is nothing can be done now. And this is the expression for the kinetic energy. Okay, so this is not Lagrangian. Okay, this is only kinetic energy we have. And what we can do is that if you don't want to write a big expression like this, we can do by introducing a particular variable. So let us say, we will say that this particular summation of the 2 masses is capital M. Okay, so that you don't have to write a big expression. And similarly, whatever appears in this particular thing, let us give the symbol. Okay, let us say, or let us call, we will call this. Okay, we will call this by some symbol mu. Okay, any symbol is okay, but mu is the traditionally people take for this. And interestingly, if you see the dimension, okay, dimensional wise, you see M1 is kilogram. So kilogram into kilogram divided by kilogram. So ultimately it is a kilogram only, not a problem. So it's a mass. Okay, so capital M is 1 mass and small m is another mass. And we will call this by the symbol mu and give the name. We are going to give the name. Okay, we are going to give the name reduced mass. And why we are giving this name? Okay, that's fine. We'll tell you. But whether you are going to give the name or you don't give the name, it doesn't matter. Finally, this is the equation that you have. So let me write down some number. Okay, some equation number 5. Equation number 5 will not change whether you give the name reduced mass or you don't give the name. Okay, we give the name and then write down in a simplified way. Now the equation looks somewhat small in the sense that I am going to put a m here, and then you will be having r vector dot square. Then the second term will look like 1 by 2. This entire expression, we will call this by the name reduced mass. Okay, and then we have this script r dot square. But then why it is called reduced mass? Why we should give this kind of what is reducing actually? Now mass will not reduce, right? If I have a mass of the sun and a mass of the earth, okay, mass will not reduce because you are doing the calculation. But then what is the idea here is that this is the idea. Suppose if you have a number 7, well, let me take two numbers here. So if you take one number 7 and another number 12, I'll take another number 12. You take any two number, okay, doesn't matter what number you take. Then if you perform this calculation, what calculation you're doing? I'm taking the product of the two numbers in the numerator and the addition of the two numbers in the denominator. Okay, product of the two numbers in the numerator and then addition of the two numbers in the denominator. And if you take a calculator, and find out how much is this. Okay, if you take a calculator and find out the answer, okay, whatever I'll write down that this is the answer. This answer will be less than 7. And not only that, this answer will be less than 12 because 7 and 12 are the two numbers that you have taken. The answer that you are going to, you take a calculator and then do it, then you will discover that the number final answer is going to be less than the first number. It is also less than them. So now what happened is we got an answer. So we got an answer which is less than your starting value. What is your starting value? M1, M2. So this is your M1 and that was your M2. So if this is your M1 and M2, my answer means the whatever M1, M2 by M1 plus M2. Okay, that quantity is going to be less than any of the M1 and M2. And that means I'm going to get a number which is smaller than that. And therefore, it apparently the value, numerical value is going to be much less than the original values M1 and M2. But still the dimensions is, you see the dimensions are the same as the kilogram, same kilogram. So therefore, we say that numerically it is a small number and therefore we say reduced. Numerically it is a small number, smaller than M1, smaller than M2. And therefore we say that it is reduced, but however, the dimension is still kilogram only and therefore we say mass, reduced mass. So now you understand why it is given that name. And that's all. And now ultimately we have the kinetic energy term written down like this, and therefore quickly we can write down the Lagrangian, which is nothing but you'll have to only subtract the potential energy, and therefore we can now write down that this is half mr dot square plus you write half mu, then you get a script r dot square, then minus the potential energy v of the script r, which is a scalar function. So ultimately let us say that this is your equation number 6. So finally what happened is that we have done some calculation and we got the new Lagrangian. So let me write down that this is the new Lagrangian. This is the new Lagrangian in terms of the center of mass r, because r vector is the center of mass vector, and the distance of separation of the two masses script r. Okay, so what do you mean by that is that the point to be noted is that r1 vector, r2 vector, these two vectors have disappeared. That means we have eliminated. That's all about it. And finally, we have a new Lagrangian given by equation number 6. So let me put a box here because that is one of the main conclusions we have. So equation number 6 is your new Lagrangian. Okay, that's fine. But what is your original Lagrangian that we have done in the last class? That we started with the Lagrangian given by equation number 3. So this is the one that you should remember. So now we have two Lagrangians. Either you use the equation number 3 and then solve the problem. Okay, that's fine. Otherwise what you do is you throw the equation number 3 and take the new equation you got, which is the equation number 6. and then you solve the problem. So either you choose that way or you choose this way, whichever is convenient for you. The point is that the solution will not change, the final conclusion will not change, the physics will not change, nothing will change. What is that we are going to change is the mathematics. That means how complicated the equation is going to be, or how elegant the terms in the equations will be. That will change. Okay, so because of that reason only we are performing this kind of calculation based on the center of mass. So now the idea is very clear that you have to say either of them. So the conclusion is this. So either you have to use equation number 3 for the Lagrangian, otherwise use the equation number 6 for the Lagrangian. Both of them are same Lagrangian, and then proceed further for the calculation. That's the meaning. So if we are going to proceed like this, then what is going to happen? So that is the discussion that we have to do. Only if you discuss, we can tell whether the equation number 3 is advantageous or equation 6 is advantageous. So you will be knowing which is advantageous, and based on that, we can proceed our further calculations. So if you are going to use the equation number 3, you will be having an R1 vector, and then you will be having an R2 vector. So R1 vector will require, or it requires, the x1 component, x2, sorry, not x2, it is y1, right? Because first one. So x1, I'll say y1, z1. You need 3 of them. And similarly, the R2 also requires 3 of them. I'll say that this is x2, then y2 and z2, which means that the clarity that you are going to get it from this kind of analysis is that if you are going to choose this particular equation, we will be ending up with the 6 number of degrees of freedom. So this is the conclusion. Okay. Now you repeat the understanding in the case of the new equation. In the case of the new equation, what happens is I require the center of mass capital R, and at the same time I need the vector small r. So now anything has reduced, or that you still have the same. That's what you'll have to understand. And for that, you'll have to better see the diagram so that you know what is R vector. So this is a capital R vector. And the entire thing is, the dynamics is taking place in the space, namely the 3-dimensional Euclidean space, the normal physical space that you have. So when you are going to have a vector in the usual 3-dimensional space, then capital R vector requires 3 variables. X component, Y component, Z component. So 3 of them are required. In addition to that, you need this R vector, the script R vector. Once again, what happens is script R vector is also a vector in the 3 dimension. And therefore, what happens is that you need 3 components are required. So ultimately, what happens is this also requires the 3 components, namely X component, Y component, Z component. This also you need 3 components. You cannot say that I will evaluate without R1 and R2. So unfortunately, what happens is this script R that you have written down here, this being a line here, you cannot have the script R without knowing the 3 values for R2 and 3 values for R1. So ultimately what happens is that even though you have written down the script R vector, it being located in the 3 dimensions, we need 3 of them. So ultimately what happens is that whether it is fortunate or unfortunate, whatever be the case, our conclusion is that this kind of study is also requiring 6 degrees of freedoms are required for this problem. So now the question therefore comes, then what is that we have done till now? Okay. We were thinking that if you do the center of mass problem, some number of degrees of freedom will reduce. That is what we were thinking. But now what happened is you have again 6 degrees of freedom. So the question therefore is that the question is straightforward question, whether all the work that we have done is simply waste or that you can do anything better. So that is the question. And for that you'll have to think once again. Now the thinking is what can be done further if you want to proceed further in order to reduce the number of degrees of freedom. It's all possible thinking. Okay. Ultimately everything will fail, and then you say that okay, whatever you do finally 6 degrees of freedom will be there. That situation is also possible. But what I am telling is how people are thinking and then proceeding further. That is the point I am trying to explain. So now the point is clear that whether you use equation number 3 or whether you use equation number 6, we are we are end up with using the 6 degrees of freedom, which means that the mathematics is not going to be reduced. Okay, it is the same level of mathematical difficulty you'll be having. That is the conclusion. Now that we are not going to leave it at this point, but rather we further ask the question, okay, let this be the case. What further can we do? Okay, what further that we can do in order to reduce the number of degrees of freedom? That is the question that we ask. And now we get a new thinking. So this is the place where you are now thinking. What are you thinking is that this particular coordinate system, you see that this coordinate is there, x comma y comma z. This is the place where you have kept. Place means origin. You have chosen an origin and fixed the coordinate there, right? Then you ask the question, why are you keeping it here? Why don't you move and keep somewhere else? So the idea is that you move this particular coordinate and then keep it here. So that is what we are going to ask the question. Or you think, so why should I keep the coordinate here and then struggle? Let me move the coordinate, the entire coordinate system with the 3 axes I'll move and then keep it at the center of the mass M1. See here, I'll keep it like this. If you keep it like that, then how the coordinates will look like? I will not draw once again, because the whole thing will, the entire thing will appear a little bit clumsy, and therefore I'll just show a dotted line here. I'll show a dotted line. Now you're able to see the x-axis there, and then some kind of an axis that you're able to see. Okay, I'm simply showing the 3 possible axes in blue color. That means you now understand what we are doing. You are essentially making a translation of. You simply move the coordinates and then keep it in such a manner that the origin of the coordinate system is coinciding with the center of the mass 1. Okay, it is not center of mass. See, this point you have to remember. Center of mass is here. This is the center of mass. But our idea is that let us attach it to the mass M1. That is what we are planning to think. Now, so if you do that, what will happen? So this is the place where we are thinking and then making a further step here. So let me therefore write down here what can be done. So that is the point I'm trying to write down. So let us therefore move. So let us move the coordinates. Move means translation. Okay, you can simply translate the coordinates. And then where are you going to fix? And we are going to fix. Okay, fix at the mass M1. Okay, so which means that we are not going to talk about anything with the center of mass to do with that. Center of mass is different and mass M1 is different. So please remember what is there in the diagram. This is the center of mass. You are able to follow the white color cursor, right? That is the center of mass. That center of mass will be there. It will not change. Center of mass will not change because of the moving of this coordinate. That point will be there. Okay, but the numerical value of the length will change. But when the coordinate is here, you have to measure the distance in the pink color. When this particular coordinate is coming here, then you have to measure this distance. That's all about it. But the point itself will not change. Okay, this particular point, that will not change. That is what we mean to say. The physics will not change. Okay, so fine. Now the ideas are clear now. So if you are going to move there, then what happens? So let us therefore move the coordinates. We are going to move the moving means translating the coordinate, and then fix the origin of the coordinate system such that it lies with M1. So if it is the case, how it is going to look like, I'll draw a rough diagram. May not be very neat. Okay, this is okay. At least you will be able to imagine what is happening. So this will be the new coordinate system that you'll be having. And then I can join the 2 lines like that, and that's all about it. So your diagram becomes very simple, and this could be the center of mass. So that is okay. So this is the center of mass. So now the diagram looks somewhat very simple now. But now in order to proceed further, you'll have to identify what happens to the other variables. Okay. So now therefore what happens is, these are the old variables. Old variable means before the coordinate movement. New variable means the variables after the this new coordinate. I will say that this is the new. So this is the new coordinates The old coordinate is the previous diagram which you have in the last class. So what the question that I am asking is, what happened to the R1 vector? What happened? That is the question. And similarly, you tell me what happened to the R2 vector. So that is what is important, and you'll have to identify them. So let us go back to the diagram and ask the question. What will happen to this R1 vector? What will happen? If this is moving and coming here and then taking this as the origin, then the entire length R1 is going to be 0, because there is nothing will be there. This distance itself will disappear. And therefore, R1 vector will go to 0. That is the first point. Remember, I'll write down here. Later we can copy it there. Okay, R1 vector will become 0. Okay, after translation. After translation. So R1 is fine. Then what will happen to R2? You have to think. I am moving this one and keeping it here. When you are moving this one and then keeping it here, what happens to R2? R2 will come and this particular line will come and join with the yellow color line. That means the R2 vector will be exactly coinciding with the yellow color line that is there. This is the yellow color line. It will match. If it is matching, then what will happen? It becomes a small r. Therefore, what happens is that the small r and the R2 will become identically same. That means R2 vector will be just overlapping on top of the yellow color line. And that is exactly, you understand, right? When R1 goes to 0, R equal to R2. Here itself it is there. This equation itself tells you that. So this is one change that is going to happen. And this is the second change that is going to happen. Okay. Once these two things are clear, now I can write down here that R1 is going to be 0. 0 means 0 vector, by the way. And R2 is going to become the script R vector. So this is the interesting thing, and therefore what happens is that there is a consequence. So I'll tell you the consequence because of this. So these are the two things that are clear. Center of mass, well, the center of mass will be now this distance. So there will be some kind of a distance from here to here, right? That distance will be there for the center of mass, capital R. It will be the new value, capital R. Okay, that's fine. So now, right now, we will not discuss that. We will go further, and then when appropriate time comes, I will explain that. So now this is our conclusion, that after making the coordinate shifting means movement. When you move it to the new place, R1 vector becomes 0 vector, R2 vector becomes the script R vector. So this combination requires three components. Three components for R vector. Is this clear to you? So this is very important. How it has come to three components? This requires three component means what? For 0, I don't want. That means earlier you said that 3 are required for R1 and 3 are required for R2. Isn't it? So now 3 of them has disappeared. You don't require anything because 0, and then R2 requires only 3 components. So what is that R? This is the R vector. So R vector is this direction. So you have this direction, and this is the arrow that you have representing the R vector, and this is the origin. So you have an origin and you have one line. That line is the vector, and this is the R vector requiring 3 components. So the 3 components are Rx, okay, I cap plus the Y component, J cap plus RZ, K cap. That is what I mean to say. So only 3 components are required for the specification. So which means that, so what is the conclusion therefore is that, so we need, so that is what I mean to say, one of them gone to 0, no? Because of that reason only. One of the vector has gone to 0, therefore 3 components have disappeared. So finally what happened is we have 3 degrees of freedom problem. So therefore we are at least, now we are happy that 6 degrees of freedom problem has come down to 3 degrees of freedom problem. So therefore, this is the important conclusion, provided that you are going to shift the origin. So that is the point to be noted. So therefore, we will now write down this at the end of this. So equation number 6, I will write down that this one. Okay. So after the translation of coordinates. Okay, equation number 6 is a 3 degrees of freedom problem. So this is our conclusion, that ultimately we were at least now successful in specifying the number of coordinates required. It becomes 3 degrees of freedom. Now, in particular, I will now explain. Practically, there is another advantage is there, that this capital R dot is not going to play a serious role in our dynamics. Okay, so therefore, ultimately, we don't require the value of the R dot itself, because we have moved the coordinate system to the R. Capital R dot will not play a big role. I will explain how it will not play a big role, but for the time being, you keep this point, that our conclusion is that only this is the one which is going to play the role, which is going to take the 3 degrees of freedom. The capital R is not going to play a role, and therefore we will not add additional degrees of freedom because of that. Okay, I will tell how it is not going to affect. That point I will tell by taking some numerical numbers. Only then you will be able to understand. Okay, so this was the important conclusion, that our central force problem is ultimately in the 3-dimensional space is a 3 degrees of freedom problem. Okay, without specifying any kind of potential. Without specifying any kind of potential. We will see what happens if you take a gravitational potential. So that is a special case. Okay, that means you'll have to further discuss what happens if you take gravitational potential. So those points we will discuss in the next class. So today we have made some progress, in the sense that 6 degree of freedom has come to 3 degree of freedom problem. To that extent we are happy. Okay. So in the next class what we will discuss is how the capital R is not going to play a big role. So that is first thing. Second thing is what happens if you choose V of R. We can choose V of R anything, right? So out of the infinitely many possibilities for the capital V of R, we will choose a gravitational potential, and in that case, whether anything special happens or not. Okay, that we will discuss in the next class.